In section 7.1, dealing with applications of differential equations, what we have here is we have this equation, and this equation represents when we have a current size, which is equal to the initial size times the base of e to the exponent of a constant times time. So the equation looks like the following. So y represents the current size, c is this initial size, e is the base, a is the constant, and t is time. Now if we take a derivative of that function, we would get y prime equal to a times c, a base of e to the power of at. Now if we back substitute, meaning that if we know that c, e, a to the t actually equals y, then we can then substitute that to be y. So y prime is equal to the constant a times y. So this y prime represents the slope or the rate of growth, which is equal to a, which is the constant, times y, which is the current size. So then we would basically say that the rate of growth is proportional to the current size. Now, when we use these two formulas, the one thing we need to make note is that whenever the value of t in the exponent is equal to 0, that would then determine the initial size. So let's take a look at an example here. It says an art collection grows in values at a continuous 5% per year rate. The initial value is 25,000. We want to estimate the value after 10 years. Now we know that our derivative function here, y prime, is equal to the rate a, which is 0.05 y. Now if we want to use this formula here, we have y, which is equal to c e to the at. We want to find out what is the value after 10 years. So we're looking for y, where we know that c represents 25,000, a is the rate, and t represents the time. So y is going to equal 25,000 times the base of e to the power of 0.05 times 10, which gives us $41,218.